Hi, you guys. Today we're going to go ahead and get started on Unit 4. We are going to actually go through these first 4 sections of Unit 4 today, talking about just some intro about reactions. Our main thing is going to be right here, net ionic equations, and talking about different types of reactions. So in Unit 4, there are actually 3 different types of reactions that we're going to talk about. There are going to be precipitation reactions, and there's going to be acid-base reactions, and then there's going to be oxidation-reduction reactions. So let's go ahead and get started with precipitation reactions today. Before we get started on those different types of reactions, let's just do a quick review of how we know if a chemical reaction has taken place. So how do we know the difference between what is called a physical change and a chemical change? Has to do with the different observations that we can make. So first of all, physical changes, they occur when a substance undergoes a change in properties, but not a change in composition. So the chemical composition doesn't change. The most common example of this is going to be a phase change, where you have something changing from a solid to a liquid to a gas. Think about water molecules changing from ice to liquid water to water vapor. The whole time it is going to stay H2O. That doesn't change, but the actual physical properties change. Also, forming, separating mixtures, those are all physical changes as well. Those techniques that we talked about in Unit 3, chromatography, distillation, those would all be physical changes when we separate those mixtures. Chemical changes, when we get substances transforming into new substances with different compositions, so the chemical formulas actually change. There are some indicators during a chemical reaction that will let us know that a chemical reaction has taken place. If heat is either absorbed or released, endothermic, exothermic reactions. Sometimes if you see a gas being formed, that bubbling, that can indicate a new substance being formed. The formation of a precipitate, this is where we're going to spend a lot of our time today. So a precipitate is, here's what happens with precipitation reactions. You might take 2 solutions. So let's remember our symbols. When you see AQ next to something in a chemical reaction, it means aqueous. It means dissolved in water. And if you take 2 aqueous solutions where you have some solid dissolved in water, and you mix those 2 solutions together, then you sometimes will get a solid that is produced, and that solid is called a precipitate when you have a solid that forms out of 2 liquid solutions. Also, color changes can sometimes be an indicator of a chemical reaction. All right, in order to write out the reactions that we're going to be writing out here in just a second, we have to remember how to balance chemical equations. So remember, when you are balancing chemical equations, that it is important for you to have the same number of atoms of each element on each side of the equation. And so I'm just going to do a quick example. You guys have done balancing equations before. A quick reminder, and it does make sense, just that you're going to go ahead and start by counting how many of each element you have on each side of the reaction. So over here on the left side of the reaction, I have 2 hydrogens and I have 2 oxygens. Over on the right side, I have 2 hydrogens, but only 1 oxygen. And so I need to make those equal. And so what I can do is, remember, you cannot change subscripts. That's really important, but we're going to add coefficients. Coefficients go in the front of the chemical formula. And so what that's going to look like is, if I go ahead and I take a 2 and I put it right in front of H2O, then that 2 is going to count for both the hydrogen and the oxygen. So now with the 2 in front, I'm going to multiply 2 times 2 is going to give me 4 hydrogens. And sorry, I'm at school, they rang the bell. So that's going to give me 4 hydrogens, and then the 2 times 1 for oxygen is going to give me now 2 oxygens. So I've got 4 and 2 over on the right side. So now my oxygens match, so I'm good there, but my hydrogens do not. I only have 2 on the left and I have 4 on the right. So I need to go ahead and put a 2 in front of H2. That will now give me 4 hydrogens. So you can count by, or you can start, by counting how many of everything you have on each side of the reaction. add coefficients until those numbers all become equal. Just a quick note to you guys on the bottom of that page where it says the practice and it asks you to write and balance the equation showing the reaction between iron 3 oxide and carbon monoxide. I think there's something wrong in the wording of that question because that equation, when you write it correctly, actually can't be balanced. So go ahead and skip that for now, and let's go ahead and go to the next page. Okay, we're going to go ahead and get into our precipitation reactions now. So this table right here, super important, solubility rules. They are going to tell us what compounds are going to always dissolve in water and what compounds are not going to dissolve in water. The reason why that's going to be important is if it's a soluble compound, then it's not going to be a precipitate. So we're going to be writing chemical reactions and we're going to have to figure out what the precipitate or the solid product is that formed. And so if it is soluble based on this chart, then it's not going to be a precipitate. If it's insoluble, then that's how we're going to know what our precipitate is from our chemical reaction. So there are only a handful of these that you actually need to memorize, and it's these right here. You need to memorize these compounds as always being soluble. So any compound that has an alkali metal, so lithium, sodium, potassium, rubidium, cesium, any compound that has any of those is always going to be soluble. Also ammonium compounds. Oh, you know what? I needed to extend this just a little bit further. You need to know nitrates. Nitrates are huge. When we're talking about solubility, nitrates are always going to be soluble in addition to those alkali metals, which means that if you have a compound that has any of those things, an alkali metal or a nitrate, it is never going to be part of the precipitate. So taking a look at these, I'm going to have you guys do some of them, but let me just kind of pick an example here. Let's look at part D. Okay, barium sulfate. What I want to do is I want to go through on my solubility chart and I want to find where it either says barium or sulfate. So as I go down my chart, I see that there are sulfates here. Sulfates are usually soluble. So this top part of my chart represents compounds that are usually soluble right here. The bottom part of my chart represents compounds that are usually insoluble. So sulfates will usually dissolve, except there are exceptions, except for if the sulfate is attached to silver, calcium, strontium, barium, mercury, and lead. So barium is one of those exceptions. So that's going to make this an insoluble compound. So you guys can go ahead and put I for insoluble or S for soluble. Go ahead and just take a look at this chart, and I want you to complete A through J in your notes, determining if these compounds are soluble or insoluble based on the rules that you see in the solubility chart. And then we'll come back in class and we'll see what you come up with for the solubilities of these compounds. Okay, now with precipitation reactions, we're going to be given the two solutions that are going to be mixed together, and we're going to have to be able to write the reactions, balance the reactions. We're going to have to figure out which one is the precipitate from our two products. So let's take a look at this one. We're going to have lead 2 nitrate and potassium iodide. Those two solutions are going to be mixed together. So you see aqueous here. So here's what we're going to do. The first thing I need to do is figure out what ions are present in each of these compounds. So this goes back to like our very first week of school when we were naming compounds, and this is lead 2 nitrate. This is the lead ion with a positive 2 charge, and I know that because nitrate, these are your polyatomic ions that you need to know. Nitrate has a -1 charge. So that's why I need 2 of them to balance out my charges. I also have potassium with a positive 1 charge, iodine with a -1 charge. So these are going to be precipitation reactions, are going to be double replacement reactions, which means that they're going to switch partners basically. So lead was originally attached to nitrate, but now lead is going to go ahead and attach to iodine, and potassium and nitrate are going to connect with each other. So I need to write those formulas correctly. If I have lead 2 and iodine with a -1 charge, that's going to give me a product that looks like this. PbI2, remember our crisscross method with a 2 plus and -1, that's going to give me PbI2. My other product is going to be, I've got K plus and NO3, so that's KNO3. So my first step is to do my double replacement. That's what this is called, is when we switch partners. And then I need to create the correct formulas of my product. My second step, my two products, my second step is to figure out which one is soluble, which one is insoluble. So potassium nitrate, remember alkali metals and nitrates are always soluble, which means that this is never going to be a precipitate. It's just going to dissolve in water. It's going to remain aqueous in the solution. But lead 2 iodide, lead is an exception for the iodine solubility rules. So this is going to be, because this is an insoluble compound, this is going to be my solid precipitate. The other thing I need to make sure that I do, you guys, is I need to make sure that I balance the equation. And so over on the left side, I have 1 lead. Over on the right side, I have 1 lead. But I have 2 nitrates on the left. So I'm going to go ahead and put a 2 in front over here. That's going to give me 2 nitrates. It also gives me 2 potassiums. So I need to come over here and put a 2 here as well, which will give me 2 potassiums and 2 iodines, which matches my 2 iodines right there. So that is my balanced equation for the reaction between lead 2 nitrate and potassium iodide. Okay, this is called, when we write the overall reaction like this is called the molecular equation. So kind of just the overall big picture. Now we're going to do some things with this to break it down a little bit more. So my next step is going to be to take my overall molecular equation and break it apart into ions for all of the things that are soluble. So you guys can see this up higher in your notes, but I'm going to go ahead and I'm going to break apart lead nitrate first. And lead nitrate is going to break apart into lead ions. I have 2 nitrate ions. So I need to make sure that I take that 2 and put it in the front to show that I have 2 nitrate ions there. Potassium iodide with the 2 in the front is going to break apart into 2 potassium iodide positive ions and 2 iodide ions. Okay, over on the right side, I have my lead iodide. Your precipitate is not going to break apart. It is not soluble, so it doesn't break apart into ions. It stays together. The other thing I have over on my right side is potassium nitrate, and there's 2 of those, so that's going to break apart into 2 potassiums and 2 nitrates. It does that because it is a soluble compound. This is called my ionic equation. And then my next step is going to be to take what are called the spectator ions. Spectator ions are the ones that are the same on both sides. So this would be, if it asked you for the ionic equation, this would be our answer. But to get us to the next step, when we write the net ionic equation, we're going to cross out spectator ions. So let's see, I've got 2 potassiums on the left, 2 potassiums on the right. I've got 2 nitrates on the left and 2 nitrates on the right. So all of those will cancel. I can't cancel anything else. So those are called my spectator ions because they don't participate in the reaction. They just kind of watch everything else as they react. Okay, so this is going to give me, for my net ionic equation, after I cross out my spectator ions, I'm going to go ahead and write what I have left over. And usually I take everything and rearrange it so that my positive ion is written first. So lead 2 plus 2I minus, and that's going to give me PbI2. And that is my net ionic equation, which shows the overall reaction that takes place while everything else is just kind of still floating around in the solution. We should go ahead and put solid right here. They're not super picky about you labeling aqueous on everything, technically these would all be dissolved in water. They're not picky about those labels, but your solid precipitate you should always label. All right, quick practice for you guys. Work on this one in your notes: potassium sulfate, barium nitrate. Go ahead and figure out what those products are going to be. Write your molecular equation, your ionic equation, and your net ionic equation. All right, we're going to go ahead and continue on with section 4.3, where we are going to take a look at representations of different reactions that take place. So we're going to be looking at these particulate diagrams again, and remembering that every time we see boxes with circles in them, that we should count everything that is there. So let's look at the example question first. It says the particle level representation of the mixture of NO and NO2 in the flask at the completion of the reaction is shown below in the box on the right. So in this box over here, I have everything after the reaction has taken place. In the box below on the left, draw the particle level representation of the reactant mixture of nitrogen monoxide and oxygen gas. That will give us that product. So let's go ahead and start with counting. That's what we should always do. Okay, so first of all, I see these NO molecules right here that have one nitrogen, one oxygen. So let me count how many of those I have. I have 1, 2, 3, 4 NO molecules after the reaction. And I have, these are NO2 molecules, 1, 2, 3, 4. Helps me to cross them out as I count them. So there's 4 NO2 molecules, there's 4 NO molecules. So what I need to think about, first of all, is on my reactant side of the equation, there's only NO2 as a product. So that means that there is extra nitrogen monoxide that doesn't get reacted. That's why it's left over at the end. So if I have 4, sorry, that doesn't look good, 4 NO2 molecules, I want to look at this mole ratio. So my ratio is 2 to 1 to 2. So if there are 4 of those, then that means I'm going to need 2 of those to make 4 nitrogen dioxides, and I'm going to need 4 nitrogen monoxides to make 4 nitrogen dioxides. Since this is how many my NO2 that I have 4 of those NO2s. So that's going to give me the fact that I am going to need 4 NO molecules. So here are my 4 NO molecules that I need to make my 4 NO2 molecules. I need 2 O2 molecules. So there's my 2 O2 molecules, but so this is how many I need to actually make 4 NO2 molecules, but there are 4 NO molecules that are extra that do not react. So I need to show those over here in my reactant mixture to show that they're there to begin with, but that they just don't get used up in the reaction. I need 8 total NO molecules. 4 of those will be used up to make NO2. 2 oxygen molecules, which all of them will be used up to make NO2. And all of them are going to be used up because I don't have any extras over here in my product side diagram. Okay, for this practice question, this is going to be the decomposition of hydrogen peroxide. So hydrogen peroxide is H2O2, and it is going to decompose into water and oxygen gas. Balanced equation for that, I'm going to need a 2 in front of H2O and a 2 in front of H2O2. That'll balance everything. So it says if I have 4 molecules of H2O2 to start out with, draw a particle diagram in the box on the right that represents the products. So instead of 2 of these, I'm going to be starting with 4 hydrogen peroxide molecules. So you need to think about what is that going to create in terms of water molecules and oxygen molecules. Sorry, I ran out of room. And you need to draw those over here in your box on the right. So go ahead and take a minute to complete that particulate diagram. This last section of our notes, we've kind of already talked about the difference between chemical and physical at the beginning of the video today. Chemical process is when you're actually breaking bonds and forming new bonds to create new substances. Physical processes only you're not breaking bonds, but you're breaking intermolecular forces. Those are our phase changes, going from solid to liquid to gas. You're not breaking any bonds there, just separating things, breaking those intermolecular forces. When substances dissolve, it can actually fit into either category as a chemical or physical process, because you are taking those ionic compounds like NaCl and you're breaking them apart into two ions. So you are breaking an ionic bond there to get your sodium ions and chloride ions. And then you get ion dipole interactions formed with our water molecules, which we talked about in Unit 3. So you guys, that is it for this section of video notes. We're going to do some practice in class with writing net ionic equations and stuff with our precipitation reactions. And then we'll look forward into the next sections of Unit 4, which is stoichiometry, a review of those things that you hopefully have done a little bit of in years past. So I will see you guys in class and hope you guys are having a good day. Talk to you later. Bye.